Okay, this is Jonathan Doolin. I'm continuing with my reaction video to planetary planetary core and surface temperatures, a paper published in SSRN Electronic Journal, January 2013. And I'm just getting ready to come to section 2, the problems with the greenhouse conjecture. And he starts out by saying, the so-called greenhouse effect is based on the concept that the sun warms the surface of a planet, and then that surface cools at a rate governed by the composition of the atmosphere. Okay, so once again, I want to go back to what I felt was my description of the greenhouse effect, and we'll compare it to Douglas Cotton's description. What I said is a thermal gradient is caused by a partially transparent medium, which allows free radiation of high frequency but blocks radiation of lower frequency. He says that the surface of a planet is warmed by the sun and then cools at a rate governed by the composition of the atmosphere. Is there anything wrong with that description? Are they identical? Is there any notable differences? Can we draw a distinction between these two different ideas? And I think there may be a slight difference because in my description the surface is not cooling, actually. It's not governed, the surface is not cooling at all. And why is it not cooling? Well, cooling implies that there is a loss of temperature or a net loss of heat over time. The version I have is compatible with the amount of heat in being equal to the amount of heat out. His description is basically saying that the rate is governed by the rate of heat coming out is governed by the composition of the atmosphere, which isn't quite the same. This is just the heat in and the heat out are the same, but the equilibrium temperature. Let me describe it this way. The temperature governing this equilibrium is done under the insulating layers of the atmosphere. So here, the way he described it, the surface is warmed by the sun and then cools at a rate governed by the composition of the atmosphere. This version describes the heat in and heat out as though they are not in equilibrium. Okay, so we got through the first sentence, and I wanted to make those distinctions of kind of just a little bit of a difference there where how he's describing things in terms of a non-equilibrium in heat transfer. Then he says the rate of cooling is thought to have something to do with the amount of upwelling radiation absorbed by the atmosphere and or the amount of energy which then returns to the surface by way of radiation. Basic question of whether this is a good description or not is whether I can replace some words with the word blanket. So we got the rate of cooling, and we're thinking of this person under a blanket of the body is thought to have something to do with the amount of upwelling, and let's just call it conduction instead of radiation. Upwelling heat absorbed by the blanket, and or the amount of let's go ahead and call it heat which then returns to the body by way, and we're going to go ahead and replace that by conduction. And then I think we've constructed a pretty well good description of what the insulation effect actually is. The rate of cooling of the body is thought to have something to do with the amount of upwelling heat absorbed by the blanket and the amount of heat which then returns to the body by way of conduction. And yeah, that is basically a description of insulation. And that is essentially what the greenhouse effect is, ignoring the part, the greenhouse effect. Basically, to get to the greenhouse effect from the description of insulation, you just add the idea of heat transfer via visible light radiation from above. And then you take that idea and add the insulation due to infrared light, and then you've got basically a viable description of what the greenhouse effect actually is. So what's he saying next? But quite apart from radiation, there is also the transferred from the surface to the atmosphere by non-radiative process. Then that's essentially, well, okay, he's not going to talk about conduction now. He's not going to talk about, unfortunately, actually, this gets a little bit painful now. All right. Okay. Quite apart from radiation, heat is also transferred from the surface by non-radiative processes. There's basically two processes besides radiation. One I've already mentioned, which is insulation or conduction. And I'm going to give two kind of definitions of conduction. One of them that I haven't mentioned before, molecules transferring heat by colliding with each other. That's kind of what you usually think of how heat conduction works. You got two surfaces right next to each other. The two surfaces directly, the heat transfers directly through that surface, and you get the molecules colliding with each other. The description of conduction that I've been using, though, is failed radiation. Basically, in these circumstances where you have infrared light trying to climb up through the atmosphere, but it collides with the molecules, well, it's probably not going to go very far before it collides with a molecule, and it's almost as though the molecule transferred heat by colliding with each other. So there's hardly any difference between failed radiation, which is just a photon not going very far, like a photon going a very, very short distance, and molecule actually transferring heat by colliding with each other. There's like practically no phenomenological difference between these two things. Okay, that brings us to radiation, and I'll talk about two different descriptions of radiation. One, photons traveling long distances through space, and two, photons traveling long distances through transparent substances. What do these two things have in common? The commonality is that the photon does not change directions or put energy into the molecules through which it passes. And that brings us to the third form of energy transmission, which is, or heat transfer, which is called convection, where a material substance of one temperature is moved through space or through a material of another temperature. So where are we at? Heat is transferred from the surface to the atmosphere by non-radiative processes. Okay. This is, well, okay, he's saying that this is a non-radiative process. Then nitrogen and oxygen molecules play the main role of insulating the surface, whilst water vapor and carbon dioxide help to radiate energy out of the atmosphere and thus have an overall cooling effect, as we shall see in later sections. I think. Okay, let me see if I can put this in the form of like the hypothesis and alternative hypotheses. Let me tell you what my hypotheses about nitrogen and oxygen are, and like compare them to Douglas Cotton's impression of what nitrogen and oxygen, the roles these molecules play. Okay, so Douglas Cotton says oxygen and nitrogen are heat insulators, while carbon dioxide and water vapor are heat radiators. Jonathan Doolin says oxygen and nitrogen are transparent gases, while carbon dioxide and water vapor are opaque gases in infrared light. Now I think these are a little bit different. They're kind of similar because we both kind of agree that yes, carbon dioxide and water vapor are, while I say they are opaque, I also, admittedly they glow in these same frequencies, so they do radiate. But wait, he says that the water vapor and carbon dioxide have an overall cooling effect. Would you say that these guys have an overall cooling effect? I don't think so. What happens is that the heat that they're radiating, they're glowing, the radiation only goes to the immediately adjacent carbon dioxide molecule where the energy is immediately absorbed. Now, if you go all the way to the top surface of the planet where the temperature of the gas up there is minus 19 degrees Celsius, then yeah, you could say, okay, those molecules have an unobstructed radiation path, and you can say definitely that this is a cooling surface. So yeah, you can make that claim that at that boundary where the carbon dioxide ends, then that is essentially where you have the carbon dioxide radiating in the infrared and thus cooling the planet. But it took a long way to get there, and during that time it bounced back and forth quite a bit. Now, as for this question, are oxygen and nitrogen heat insulators? Let's see. Nitrogen and oxygen molecules play the main role of insulating the surface. Well, let's just try to fully acknowledge that hypothesis. Some people say air is a good insulator because it is a gaseous substance. Therefore, it is spread out. Molecular configure resists heat transfer to some degree. Yeah, here's a question. If air is one of the best insulators, why do we use fiberglass? I gotta admit, I like Stuart Coyle's answer. Insulation depends on stopping three mechanisms of heat transfer: radiation, convection, conduction, and air does nothing to stop radiation. It actually supports convection. It is much worse conductor of heat than most all solids. A vacuum is a better insulator as it does not support conduction or convection at all. This is why thermos flasks work so well. And he's mostly right when he says air does nothing to stop radiation, because air is like 70% nitrogen and something like 30% oxygen and like 1% argon, and the carbon dioxide is in the parts per million area. And but the nitrogen and the oxygen do nothing to stop radiation. And but yeah, I guess it does support conduction. It does support conduction. So oxygen stops radiation? No. Stops conduction? No. Stops convection? No. So is it a good insulator? No. And two, does it stop radiation? No. Does it stop conduction? No. Does it stop convection? No. Is it a good insulator? No. Carbon dioxide, does it stop convection? No. Does it stop radiation? In infrared, it stops infrared radiation. Does it stop conduction? Not really. There's some that basically what it blocks in infrared becomes conduction. So it's not great, but better. It's a better insulator than oxygen and nitrogen. These are literally not insulators at all. And it's really pretty much shared with all the diatomic gases, O2, N2, H2. Anything that's a diatomic gas is usually it's got that shared outer those two shared outer electrons that make them just stick together real tight, and there's just like it's just really hard for light to interact with the particle, unless you got just like this really high, unless you got some kind of really high frequency light that hits it. Most of those diatomic particles are really stable, and they're not going to stop any radiation generally. They'll end up being transparent, and they're not really going to be terribly great conductors either. You're going to find if you get out on a humid day, then you'll find that the heat from the air gets right into your body because of the presence of H2O. But if you go out on a really dry day, there's not going to be very much effect of the carbon dioxide, or I'm sorry, there's not going to be very much effect of the oxygen and nitrogen getting into your skin, not nearly as much as on a humid day. So anyway, those we can just kind of like acknowledge these models to be different. His model of nitrogen and oxygen, he's saying that his intellectual model of the nitrogen and oxygen molecules play the role of insulators. My description of nitrogen and oxygen, I don't feel like, in my mind, they're not insulators. They're terrible insulators, because they're not stopping radiation, conduction, or convection. On the other hand, water vapor is a pretty good conductor of heat compared to nitrogen and oxygen, but it is true that they do radiate energy out of the atmosphere. For instance, they can radiate water vapor. It helps to radiate energy out of the atmosphere into your skin. That's why on a humid day, you're going to find it to be colder or hotter than a non-humid day. But as far as there being an overall cooling effect, as for that representation, looking here, where you have that cooling effect as the light radiates out from the top surface of the Earth, that could be described as an overall, I've used air quotes, overall cooling effect. But that same overall cooling effect would have been the same if you had just left out all of those greenhouse gases and made this surface negative 19 degrees Celsius, and you would have had the Earth's surface at negative 19 degrees surface, and it would have been the overall cooling effect would have been at the ground air interface instead. Oh wow, so I'm 20 minutes into this video and I've only covered 2 paragraphs. And I think I only like to make my videos around 20 minutes in case there comes up some kind of problem. So I'm going to stop here and go on with the next paragraph in the next video. Sorry for it's taken me so long.